Welcome to the tutorial series for the freeCappuccino software, the CFD code. My idea is to create a series of online tutorials where I will be showing some example cases which are simulated using freeCappuccino code. Also in the future I plan to create some code walkthroughs in which I will introduce the interested people in what is happening in backstage of all these solutions that we will show in our tutorial series. And I'm doing all this to help you guys start using this code, because I think it's nice code and you can do a lot of interesting things with it. So I hope you enjoy it, and I hope I see you soon. Bye bye. Maybe the first thing I would like to start with is Rayleigh-Bénard case, which I found in OpenFOAM tutorials in latest version 2006 actually, that I'm using now. They call it Bernard cells. I know in previous versions it was RB cells, found in heat transfer and the buoyant Boussinesque pimple foam tutorials for this solver. So in freeCappuccino we do it a little bit differently, in that way that we can set parameters in our input files, and that way distinguish between what would be different solvers in Openform. So just checking, is it simple or piezo, or is it Boussinesque or not. You can have what are 4 solvers in Openform. So let's start first, if you haven't already, just compiling the code. I want to show you how fast the compilation procedure, how long does it take. So let's just type make. Okay, let's make clean first. I would like to show you I would like to show you how long does it take to compile it on my machine. This is the laptop with i5 Core i5 Intel processor and 8 gigabytes of RAM. So this is how it's going, and it is compiled. So now I'm in the RB cells folder. Over there I have a couple of files that I need to have in order to start simulation. I'm using same mesh as Openform case, so I'm using the polymesh folder with the mesh files. The only thing that is changed here is this boundary file, in which we list names of boundary conditions and specifying them in this way. Just pause and compare it with the old file. So not much difference, but only small difference. I like it more this way. So the only thing that we need to change when we use Openform meshes is to change boundary file. There's even a small utility that can help us with it, but we'll talk about it some other time. So we have mesh. Next thing we need is it's related to mesh file, is this BTK folder, which is now full. So just let me, because I already did some simulations previously. The only thing we need here is this mesh VTM and mesh file. This is actually produced by opening the Rayleigh-Bénard case of Openform in Paraview and just saving the mesh data. Why do I need this? Well, for simulation itself we don't need cell connectivity data as in Openform, but for post-processing, for writing VTM, VTU, VTK files for Paraview, because Paraview is cell-based, we need this connectivity data, which is absent in polymesh data description. So for simulation itself I use the same data as they do in Openform, but since Paraview doesn't have, of course, native reader for freeCappuccino solver as they do for Openform, I need to prepare how mesh connectivity looks. So that's why I have this VTK folder, which consists of these files. It's really easy to obtain them, so one of the next times I'll show you how do I get them. This is just to let you know that we need them. We also need zero folder as in Openform, but it's a little bit different. You can see how the description goes. So if you're familiar with Openform, it's similar to this one. You have section with internal field, then to boundary field, and every boundary is described separately, and belonging condition is if it's Dirichlet, then you need some values, or if it's Newman, you need to prescribe is it some value of gradient or it's zero gradient. So this is kind of similar to Openform, but still a little bit different. It's basically, you can see that it's modeled on that idea. My idea is to have smooth transition between these two codes for people that have some previous experience with one of these. I prepared a couple of things that I want to show you. I would like to run it like with simple algorithm, and also with Piezo algorithm. So for simple algorithm, I just call script run simple, which calls Cappuccino and gives input simple as input file. Data will be dumped in monitor file, and it will create some restart file for restarting simulation, and dot is that all other files are dumped into present folder. This is how you call the code. Maybe I'll change it in the future if it's too many data on calling line. This is this input file. A lot of parameters you set in there. So let's just go quickly through it. Title of the case. Here we set density and viscosity for this case. It's presently set to Rayleigh number of 10. So therefore we have these values for density and viscosity, same as in Openform case. These are Prandtl coefficient for laminar flow, reference temperature, and beta thermal expansion coefficient. We have buoyancy activated, so it's true here. Gravity vector is given following this data, and finally we set Boussinesq approximation to true because we want to have Boussinesq approximation active. Let's move on. Case will be transient. Therefore transient L transient is set to T, true. Also time stepping algorithm is backward differentiation of first order, so Euler implicit. For turbulence model we just set 0 because it's laminar case. Moving on, convective scheme is set to second order upwind. This linear /f is something based on Fluent documentation, Fluent theory guide. That's why I put it linear upwind, but linear /f, so it reminds you of Fluent. F here means Fluent, so this is actually what is second order upwind in Fluent. I have set the gradient limiter to Bart Jespersen. For these gamma coefficients, they are all 1. These are used in let me recall, deferred correction. Yes, we'll discuss that more in detail when we go through code and theory. Under relaxation factors are familiar values of 0.7 for velocity, 0.3 for pressure, and 0.7 for temperature. So in freeCappuccino, every field has some specific order in which is used. So for example, you can see everything with n phi values is related to some field that is calculated. First 3 are reserved for velocity, 4th is for pressure, 5th and 6th are for 2 equation models for turbulence, 7th is for temperature. So we have false for solving two equation models in turbulence, and we have true for temperature. This is for modifying viscosity, then concentration, electric potential, and so on. So if GDS of I, where I goes from 1 to n phi, every value is for certain field force. So this 1, 2, 3, first three are for velocity, fourth is for pressure, and so on. Fifth and sixth are for K and epsilon, for example, seventh for energy equation or temperature equation, and so on. These are relative factors for decrease in linear solvers. This is maximum iteration for each linear solver. Here we prescribe number of steps, time step size, after how many time steps we dump the output files, and maxit is the maximum number of outer or simple iterations within one time step. Next, we prescribe which algorithm for gradient calculation we use. We already said that when we calculate gradients, we used Barth-Jespersen for limiting. And here we have few options. We have a couple of variants for least square gradients, and simple Gauss cell-based gradient computation. So because we have simple rectilinear mesh, we'll use Gauss gradient option. These are not important at the moment, so we say here that we are using simple algorithm, and that's it. Other things if we want to fix current number and its value, but this is a quick walk through input file for this case. So because everything is controlled by one script, simple, and we'll run this case in simple mode. So we use non-stationary run, but we use simple algorithm for iteration within one time step. While we run, it will not take a while. It dumps a lot of files because it will make a lot of cases. We have like maybe 20 time steps that we will save files, so that's why it takes a little bit of time. While we do, okay, it's done. We can look at the monitor file. So if we open monitor file, it logs everything that is happening during simulation. So it's saying we have simple header when we ran the simulation. We print the input file, so you can use same conditions for making new simulation, some mesh data, and so on, data about internal fields, so and initial conditions for velocity and temperature. Here we see the program calculates minimal distance to the wall, which is not important in this moment. It is usually important for k omega SST models, for example, where distance through the wall is important. And this is typical output for iterations. We have in one block we have data about which time step and which iteration is going on. First, in the header we have what is time step number, what is time step size, and total time. We log what is the current number, mean and maximum. Then we have residuals for every field that we solve. Here this is the information about what is the algorithm used. For example, here it's by CG step with incomplete lower upper preconditioning of zeroth order. So these are the starting and final residuals, a number of iterations that is required, that was used. Later we have, in simple algorithm, we solve the U, V, and W field. Then we solve pressure correction. For that field, we used precondition conjugate gradient with incomplete Cholesky preconditioning. It required a little bit more iterations. So as you're familiar, this is the part which is maybe most intensive in computation in CFD simulations. We have data about time step continuity errors, which are a little bit different than what is shown in Openform. We'll discuss some other time. And finally, after U, V, W, and pressure correction, we solve a temperature field. So this is what is shown here. And in this line, we show what are the minimum and maximum values for these scalar fields, the additional scalar fields that we solve. So since simulation is done, we can, during simulation, we can also use this tail command and see what are the latest results. We also have script for plotting residuals. It's written for GNU plot. Let me just find it because I previously ran a couple of times the simulation. So just GNU plot residuals. This is the visual appearance of the residuals. So there's a lot of lines, therefore it looks like this. But it's a bit artistic, I don't mind it. Now we would like to see the simulation post-processing. We'll use Paraview for that. Paraview. And let us see where the data are stored. They are all stored in VTK folder. If we open it, we can see all these files written. For example, what are the basic ingredients? For example, this is boundary file. The number is related to the time step. It has including a folder 50, and we have solution fields 50. So these are all fields, internal and boundary fields in solution fields 50. These are only boundary fields. And in folder we have VTU files with the interior and with each separate boundary. So this is the structure. For creating these files, we use geometry data already provided with mesh VTM file for Paraview. So we'll just hit Paraview. Okay, we did already, and let's just enter VTK folder and choose. We have these solution fields from 50 to 1000. We'll collect all of these because we want to see the evolution in time of our case. We just hit apply, and this is it. For example, for initial value for temperature, there's one thing which is interesting. Here we plot cell data. That's why the picture won't look smooth at the beginning. But first we have T, and let's just play and see the animation how a flow evolves regarding temperature fields. So let's check play. So you can see actually with a Rayleigh number of 10, we have these convective rolls appearing. This is temperature field. If we switch to U velocity, you can see these convective rolls. From magnitude, we'll switch to X component and Y component. This is really coarse mesh, as you can see. So things about the number of these rolls may change once we make finer mesh. But it's left for some future video. I would like to go now to filter, and I will find cell data to point data filter, which will enable me to interpolate all these cell-centered values to nodes. And when they plot nodal data, it is smooth for some reason, unlike the cell data, because they probably consider that cell data is coming from finite volume algorithm, where value is constant throughout the cell. So let's go back and see the evolution once again with this picture, smooth representation. Let's change the color scheme to jet, Okay, close. Let's move legend here. And this is the final solution. So let us compare it with what is obtained in Openform. We'll open their case. I already did that and saved the images for final time step. And this is it. So if you compare these two, they look very similar, but there are small differences, which I will show you. If you can see, the number of these peaks here is the same. There are 6 of them, although in our case there may be more wide than in the case of Openform. But probably this is because we have really coarse mesh, and this is something that happens also in high order codes. I was reading an article about Rayleigh-Bénard case for spectral element code NEC 5000 by Paul Fisher, and he said that number of rows was very sensitive to the order of the spectral elements he was using. So he set order of 7 in one case, so he would get the proper number of rows. So this case is sensitive to the data, so no wonder there is slight difference here. Now let us move to other thing. As I said, by changing certain parameters, here we used something that would be equivalent to buoyant Boussinesque simple foam, except that in freeCappuccino we can use it also in non-stationary mode. So in Openform, when you say that you're using simple, it's only for stationary runs, as I understand. Correct me if I'm wrong. For non-stationary runs, they use Piezo or Pimple algorithm. The thing that we have here is, I don't like the word pimple, so we have only Piezo algorithm, but it has an option for under relaxation of pressure and velocity fields. So you can, by switching some parameters, you can get what is called pimple in the Openform. So still with changing of certain parameters, we can obtain what is different solver in Openform. Let's because now we will run Piezoscript, which calls different input file, input Piezo, and let's look how what is written inside. So let's open input Piezo. Same thing as previously, except that we have set here instead of simple, Piezo is set to true, and the number of Piezo corrections is set to 2. Everything else is the same. Also, maximum iteration is 1, because we have only one auto iteration. We solve momentum predictor, then we correct solving the pressure this time instead of pressure correction equation, then we correct velocity fields and mass flux, and we move on to next time step. Also in Piezo, the under relaxation factors are all 1. Previously we had 0.7 for velocities and 0.3 for pressure. Now they are all 1, and all other things are the same. We still use transient solver, we still use Boussinesque approximation. So let's run it like this until we will use 1000 time steps. But because we will store everything in the same folder, I would like just to delete data from the previous run. Let me delete this, and okay, let's run now. Run Piezo. So this would be buoyant Boussinesque Piezo form, equivalent of buoyant Boussinesque Piezo form. It's pretty fast. Let's see the residuals in graphical mode. This is how they look like. We can see the tail of the monitor file. What's different? We have only one iteration per time step. So after solving momentum predictor, we solve one pressure equation for correction, and then we repeat it again 2 times for the same momentum predictor, and after we correct velocities and pressure and move on to scalar fields. Let's see the results. Let's go to Paraview and see is something different in this case. So this is, as you can see, much faster than simple iteration, which required 10 iterations and under relaxation within time step. Let's open Paraview, open VTK, and we'll find solution fields with inner and boundary fields. Let's open it, apply. We'll do right away cell data to point data interpolation, and we'll open this point data for T. Let's move legend down there, and let's just hit play. And now again, as you can see, we have produced these convective rolls that are happening for this case. This is velocity magnitude, and this is y component, vertical component of velocity. There is still, so the case is very similar to the previous one, but there are small differences between what we have in Openform and here. For example, let us count the rolls. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we check their case, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rolls. This is the cross-section of temperature field with 6 peaks. And in our case, it's also 6 peaks, but it's a bit wider. So the difference is not much between these two codes. I think that it won't be too big if the mesh was refined. Look at this mesh, is really coarse. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cells, only 10 cells in vertical direction. So it's really coarse. But now I would like to show you one more run with slightly different settings. Once again, I want to delete everything that was produced for post-processing. Let me delete this. And now I will go into input piezo file and do slight changes. So we have what is pimple algorithm in Openform. So we will solve the same thing as in piezo. We will solve momentum predictor. Then we will form, assemble, and solve pressure instead of pressure correction equation, which is done in simple. But we will allow under relaxation of this field, and we will allow going back and performing some outer iterations. So they say it's a mix of simple and piezo algorithm. Of course, it is same here, but here we change it through parameter change. So we leave that it's piezo, but number of piezo corrections we set to 1. And just for this time, I want to show you, we will set outer number of outer corrections to 2. And here, where we set under relaxation factors, we will say 0.8 for pressure. Let's have some under relaxation for pressure field, and let's repeat once we solve everything. Let's go back once again and once again solve momentum predictor and then pressure. Everything else is the same. everything is run with run piezo. It's a little bit more time consuming than piezo because it goes for one more auto iteration. Let's see monitor. So you can see for one time step, let's make this wider. For one time step, it makes two iterations, auto iterations, going through the momentum predictor, then only one pressure, solving for pressure field, then going to scalar field for temperature, and going once again, which helps reduce residuals for pressure field. This is for this run, this is for the previous time step. So this is how actually we produce what is pimple algorithm in Openform. I would like to show you residuals, how they look right now. You can pause and inspect this image. And let's go to Paraview to see results. Open VTK, we'll find solution fields, apply. Okay, filters, recent, cell to point data, apply. So we get this nodal data, which is shown smoothly here. And let's just hit the play button. Okay. And this is what we get. This is what we get, very similar to the previous thing. Only now it is from the what is pimple algorithm in Openform. So here I have showed you how you can by changing parameters in input file, you can produce different solution methods. The code is currently going through some changes, so if there is need, I will update this tutorial, and I hope that in the near future I will have more tutorials for you, some other laminar cases, and then moving on to turbulent cases. I would like to make this introduction to this new code easy for you. In future we also will have code walkthroughs, so you see how code looks like and what is behind the scenes for producing all this. I have a lot of things for you in my plans, so hope to see you again very soon. Bye bye. Just one more thing, if you have patience for me. So let's open this input piezo code, and just let's leave everything like it was in previous case. Just let's change this number of auto iterations to 3. Let's save it, and we'll just go and simulate and overwrite the previous files. It will take a little bit more time for the simulation, but let's just do it. We'll hit run. So we see in console that VTK 50, 100 and other folders and files already exist. So overwriting them takes maybe a little bit time, but here we are done. So we're doing the same thing as previously. We're using what is called in Openform pimple algorithm. So we're using simple. We're actually using piezo with 3 auto iterations and slight under relaxation of pressure with 0.8. Let's open Paraview now. Let's point to VTK folder. Solution fields, let's open it. Apply. Filters, recent, cell data to point data, apply. To get this nodal data, vertex data, temperature field. We'll just move this down here, and let's hit play and see what's happening. This is interesting. Now I will show you why. Let's just change the color scheme to jet, And look at this. Let's compare it now to Bernard cell's case. Look at this. It's identical. Oh, just a second. I want to open this. Now these two look identical. You see this peak here is cut through the middle, and this one is left here, so we have same number of peaks. Let's do following thing. Let's count the number of rolls in y vertical velocity component. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, starting with blue, ending with the red. Let's move to u component, y, edit, change the color scheme, apply, close it, and there you are. Now it looks the same. So because of the coarse mesh, the code was a bit sensitive to the setting, but applying the setting which I described previously, now I got this almost same thing that they did in Openform. I think these two results would actually converge to the same thing if we refined the mesh. So just have in mind that this is really coarse mesh that we're using at the moment, only 10 cells in vertical direction, so it's not important so much to have identical results. But there you go. I just wanted to show you that these two things are not actually too much different. Thank you guys. See you soon.